What we're going to do is we're going to look at some of the contributions of the early workers towards the structure of the atom. We're not going to look at the contributions of everybody that did this because there are a large number of scientists that did background work that allowed us to develop our current model. But what we will do is we will touch on the major contributors. And so we'll be looking at Dalton, Thomson, Rutherford, and Bohr. And then we'll touch on the contributions of a few other important people. The first one we want to talk about is Dalton. Now, Dalton is considered to have started the modern atomic age because he reintroduced the concept of the atom and linked it to a lot of the information they had at the time in terms of the chemistry. And as you can see on the screen here, he had about approximately 5 major postulates in his theory. The main ones being atoms are tiny particles and everything is made up of atoms. Dalton's theory was very rigorous, and the only part that he was wrong on was that they are indestructible, because we know now through nuclear fusion and fission that we can rearrange them and change them from one to another. After Dalton, Thomson started to look at the model, and what he did was he took some of the knowledge that they had at the time and he used a gas discharge tube. And what this did was it allowed him to shine a beam of particles at a glass surface, and whenever the beam hit the surface, it lit up. And then he passed this beam between two magical plates. And so we can see here in the diagram, that's a sketch of what he did. And he created a beam and he had it strike the plates. And what he found was that the particles could have their paths changed depending on whether or not the magnetic field was on or the strength of the magnetic field. And so what it allowed him to do was he was able to come up with a mass to charge ratio of the particles. He called them a variety of names, but eventually we called them the electrons. And so Thomson is credited with discovering the electrons using the cathode ray tubes. Now, he knew that the overall atom was neutral, and so therefore there had to be positive material if the particle that he discovered was negatively charged. And so what he did was he said that the positively charged material surrounded the negative electrons, or that the electrons were embedded in a positive material, much like chocolate chips are embedded in a cookie. He called it the plum pudding model because plum pudding was a popular English dessert. But here we have a diagram of it. As we can see, the green represents the positive material surrounding my negatively charged particles. Now, Thomson was able to, one of the contributors that used Thomson's work was Milken. Milken's work was important because he was able, using drops of oil with a negative charge, to determine the charge on each electron, and also from his mass charge ratio to get the mass of an electron. And as we can see, both of these are very tiny values. In between and around the same time, a number of other scientists were doing some work. And we're just going to talk about two contributions of Einstein because they become important for later models. The first is that Einstein, using a variety of statistical calculations, was able to show that atoms existed. And up until this point, there was still debate as to whether atoms were real or not. And so this happened in 1905. The second thing Einstein did was he used research by another scientist and adapted it to be able to explain the photoelectric effect. And in doing so, he showed that light traveled in discrete packages that we call photons. And so he was able to use these two concepts to explain a variety of different things. And as a result, it allowed other scientists to explain the research that they were finding in terms of the structure of the atom. Now, Rutherford was a compatriot of Thomson, and he set out to show that Thomson's model was correct. He believed that Thomson's model was the correct one, and so what he did was he took some radioactive material and he had them emit radioactive particles at a thin layer of gold. Okay? And we can see in a diagram here what he did. Now, he predicted, based on Thomson's model, that all of the particles would pass through unaffected. But what he found was that some did go straight through, but others were deflected from their path, and some were reflected as well. So this meant that he had to rethink his model. So the first thing he said was that the positive material was not spread out, but it had to be condensed in a tiny center of the atom, which he called the core or the nucleus. Because most of the alpha particles went straight through, he said the atom must contain lots of empty space. Because of the ability to change the path of the alpha particle, and he knew that the mass of the electron was so small, he said that most of the mass of the atom has to be in the nucleus. Okay, and said it was dense. And he coined the term proton. And we often attribute this to the structure of his atom, because he does not state where the electrons would be, just that they would be around the nucleus. Now, one of the problems, or a major problem with Thomson's model, comes out from the fact that when particles change directions, they should be emitting light because they're accelerating. And what we're seeing is that this does not occur. When the electrons are going around the nucleus, they're not emitting light. And they're also maintaining their energy, so they're not spiraling into and collapsing into the nucleus, to which they are attracted to. So these two problems, as a result, suggested that Rutherford's model was incomplete or not correct. And so Bohr set out to investigate this. And what he did was he took research from another variety of other scientists who were looking at spectrum. In spectrum, all we do is we take light and we pass it through a prism, and then we analyze the light. And so what he did was he was studying the spectrum of hydrogen, and he used the concepts of quantum and photon from Planck and Einstein, and he came up with a model to explain it. Now, Bohr's model is said to be the first quantum model, because he said that each electron contains a specific amount of energy, which is a quantum, and this amount of energy allows them to maintain their position. And so now, as a result, when they're moving around the nucleus, they're no longer accelerating or in changing directions, and so they wouldn't be emitting light. They have a certain amount of energy. This energy causes them to maintain their position. They only offer, he called it, specific orbits around the nucleus, and they can't be found in between. And so this is why it's called a planetary model. Just like the planets are at designated locations around the sun, the electrons are at designated locations around the nucleus. Electrons can gain energy, and when they do, they can move away from the nucleus, but when they don't want to be there, so when they fall back to the nucleus, they emit light, and that's what causes the spectrums that Bohr was investigating. Okay, and so we can have, they absorb energy, they move from a orbit closer to the nucleus to an orbit further from the nucleus. They don't want to be there because they're in an excited state, so they release the energy and they fall back to their original orbit, which we call a ground state. Now, there are a couple of problems with Bohr's model. One being that it violated Heisenberg's uncertainty principle, which we knew at the time, which basically stated that we can't know both an electron's position and how it's moving because the act of measuring it will change it. A major problem with Bohr's model is that it only is valid at predicting the spectrum of hydrogen. As we move to atoms with more and more electrons, the predicted spectrum and the actual spectrum that we measure are very different. And so as a result, we had to come up with an even deeper model. Now, there are another number of other contributors. that were occurring, and one of them that's key is de Broglie. And de Broglie stated that not only can light have wave particles and light properties, wave properties, sorry, and particle properties, but that all matter can. And in doing so, he opened up the idea for the quantum mechanical model. Okay, and as we stated already, Heisenberg contributed the uncertainty principle. Basically, the act of observing or measuring will change the position or movement of an electron, and so we can never know them with certainty. So both of these contributors, plus a number of others, led Schrödinger to develop his wave equation. And Schrödinger's wave equation is a mathematical function, and what it does is it allows us to predict a region of space where we might find an electron. So if I wanted to go and look for the electron that belongs to hydrogen, Schrödinger's wave equation would give me a 3D region around the nucleus that I could look for that electron. It will not tell me exactly where that electron is or how the electron is moving, but it tells me where I might find that electron. And we can use his wave equation to predict the position of all of the electrons of an atom.